Hi, welcome to the DV Club Europe on today, 3rd of September. Our topic today is low power verification. We have a 1-hour meeting with 2 user papers on this topic. Our user papers, just for some attendance information, today we have 144 attendees. Everybody's remote. DV Club Europe is still remote at the moment. That represents 93 companies in 30 different countries, so definitely a global event rather than just Europe. As I said, we've got 2 user papers today. Satinder Paul Singh and Pavan Kumar Damala from Hermes Semiconductor first, and then Ramya and Dr. Shivanandam, from the College of Technology and the Kumarasamy College of Engineering, and they'll come on second. A quick thank you to our sponsors who still allow us to run these events. It's Agnesis, Cadence, Bracket, and Synopsys, and to Tasself, who hosts the event. Okay, so I will stop sharing and hand over to our first speakers, and I will then do the introduction. So our first speakers today are Satinder Paul Singh of Hermes Semiconductor, where he's CTO, and Pavan Kumar Damala, also of Hermes Semiconductor. He's the engineering manager. The topic is low power verification of RISC-V processors. Satinder Paul Singh champions continuous operational excellence, employing lean and agile processes and upholding quality in SoC IP implementation and flow methodologies for both established and advanced technology nodes, enhancing quality and efficiency across business units within demanding market timelines. Pavan Kumar Damala is a design verification semiconductor professional with a track record of successfully delivering large-scale SoC and IP needs. He thrives in delivering on-time and quality verification needs by coordinating with geographically diverse teams at global sites. Satinder is based in Germany and Pavan is based in India. So over to you, Satinder and Pavan. Thank you.
Yeah, thanks. Thanks, Mike. Hi. Myself, Pavan. Today I'm presenting a low power verification of RISC-V process. And Satinder will help me, and Satinder will help you on doing this one. And going forward, this is the main architecture I want to discuss about the difference between RISC and CISC process. CISC is like a complex instruction process, and RISC is for simple instructions. So as you see here, what difference it makes? First of all, why people are going for RISC instead of CISC, and we have some other process also. Why RISC? RISC is because the instruction set is very much simplified and very directly used. So which enables a faster processing. Right now, if you take in here, this is a CISC processor. In this CISC processor, you can see it is a complex instruction set. We have it. So if you want to multiply something, some A1 to A2, we are giving a simple command like A1 and A2 mult, like that command we are giving. So then this will process, and the microprogram memory will fetch that data and everything. Then it will go on like this. But it's a complex thing. So it's a complex architecture and everything. But as comes to CISC, then we have to the same command you want to give multiplication. You have to give into this like elaborated one like loading data A1, A2. Then we have to do multiplication, then storing of where we have to store the data. So it's a simple instruction set which will help you in faster processing, less complex. But problem is like problem with the RISC is like, what is the, if I want to process multiple data, so multiple command like this, so we need more memory because every instruction has to store in some particular location. So here this one is taken only max 1 or 2 bytes, but this one will take around 4 to 8 bytes. So it's storing of the same, what are the firmware what we use, right? So the firmware what we use has to storing will be more for the RISC processor. So going forward, the people who are now in the industry currently right now, people are using the hybrid processor. Like they are taking the capabilities of CISC. So some instruction sets they are getting it from CISC, and but trying to implement the same thing in the RISC. That is normally like a hybrid processor, mix of CISC and RISC. So, but while implementing the RISC, we have some challenges that we're going to discuss right now. So let's go through them. So the key challenges in designing the low power. And one more thing is like the risk is like why people are going for RISC is like it's because of simple instruction set, it will take very less memory, more memory and less power consumption. So that's why people are going for RISC. Like if you take any mobile process or something where where the power is critical. So in this type of thing, RISC is very much suggested. So, but what are the challenges in going for simple low power design? So here comes the things. Main key challenges in low power design, the power consumption, optimization. We have two types. One is dynamic power consumption and one is static power consumption. Dynamic power consumption comes like unnecessary clock gating or clock toggling, and unnecessarily we are giving power to those modules, whether we are not using or not using. So that those type of comes under dynamic power. And next comes the static power, like we are using FETs, right? So FETs have some leakage currents, those things. So they has to be on. So those are also comes under static power. Next challenge is like a power management. So here we comes in order to, so we have to do the power gating to get the power management. And doing this power gating, we have to thoroughly check which one to get and those things, and voltage scaling. So whenever there is a performance requirement, depend on the performance requirement, we do the voltage scaling. Normally, this is what people call depends upon, they will go for DVFS and everything. So we'll discuss that one going forward. And next is thermal management. As you know, right? Whenever we keep on using any of the IC, so there will be some heat dissipation will comes. So we have to use a better heat heat things and everything to get the thermal management. That's one more challenge. And designing of low power at various levels. There's two levels. One is a circuit design, one is architectural design. So while designing your circuit only, you have to think of where can I save the power, like clock gating here also and architecture also. So we have to make that whole block some clock tree management. Those things we have to take care. During the architecture only, we have to take care for low power and clock management. There comes the clock gating and clock tree design. Clock gating means like we have multiple clock gating tech features like automatic clock gating or manual clock gating. So it depends on the requirement. We'll gate the clock, and in order to get the clock, we have to create a proper clock tree structure so that we can efficiently and effectively do the clock management. And these are the main key ones. And apart from that one, we have other modes also, like software and firmware optimization, and that consists of code efficiency, like running unnecessary code also consumes power. So we have to make that one things. And sleep modes, whenever we're not using something, we have to sleep mode, like we have our mobile. So whenever we're not using, the display is going to low power, like that sleep modes we have to create. And battery life, next challenge is like battery life management. So we have to take care battery optimization techniques, like how to, I mean, uh, battery, how to optimize the battery. Different techniques are available, so it depends on the optimization techniques. Like you have batteries also, different types of lithium. In lithium ion also we have different batteries, so depends on that one. We have to take care which one to buy, which battery to choose, how much power, and what is the technique we have to do, charging and discharging techniques, everything we have to take care in life management. And one more challenge is like low power design tools and methodologies. So designing is one part, and simulating those low power designs and verifying them is the next part. The simulation of low power is a bit difficult because we have to check all the things like clock gatings and dynamic voltage switching, dynamic voltage changes, frequency changes, everything we have to take care. So the simulation and verification of them is a bit difficult, so we have to take care of that one. And the design automation tools, which tools to choose, how to verify it, whether we're covering those things or not, those things. So I'll give going forward, I will give a small glimpse about how can we do better verification of these things also coming forward slides. And There's one more thing. Challenge is like trade-off and constraints. So here is like performance versus power. How much? If you need better performance, it consumes more power. But if you less performance, it means less power. But if you want to save power, you have to choose properly your design in such a way that it has to save power things. And also, if you want to go for low power, it's a cost implication. Cost implication comes because we have to spend more money on those things. So that's the one thing. And next is like emerging technologies. So we have to go for new materials and processes where we can get like K-dielectric like that materials, and we can use them for lower leakage currents and those things. So these are the main challenges in low power design, and these are the design issues and their explanations. Uh, Power dissipation, mostly, right? Every IC will uh, consumes power. So when it's consuming power, it will generate the heat. So we have to go for better heat sink managements, thermal spreaders and advanced cooling techniques to make the heat management and leakage currents. Leakage currents means like, right, transistor. When high need transistor, it can, even though if we switch it off, some leakage current will come. So we have to make sure we have to use more proper high K dielectrics and optimizing transistor and implement. So those will implement your power, power leakage currents and those things. And the dynamic power consumptions. Dynamic power consumption means like unnecessary. We are giving clock to, switching the unnecessary. We are switching the unnecessary activities going on the transistors, which is not required. So the unnecessary switching of transistors will consume power. So we have to um, make proper clock gating and those things, and proper frequency switchings and other optimizing circuits you have to take care for dynamic power consumptions and clock gating and power gating. So we have to make sure that properly your circuit. Uh, so when necessary, if a circuit is not at all using, then we can go for clock gating or power gating. So if you design it properly during the implementation stage only, then we can save the unnecessary togglings. So which saves the dynamic power and unnecessary power gatings. So which will save the most of the power. So that's the one thing. And design complexity and verification. Uh, right, low power designs normally are much more complex and difficult to verify. We need more number of tools and more number of infrastructure to verify these things. So those things has to be taken care. And as I mentioned earlier, the trade-off between performance and power. So yes, if you reduce the power, and automatically the performance will be reduced. So we have to maintain the balance between performance and power, that has to be taken care. Uh, how to switch, when to switch, and how to monitor the activity. So when to increase the power, when to decrease the power, depends on the performance, the power consumption. We will take the power consumption. So whenever not required, performance not required, we go for low power, very low power. Low voltage, like low frequency, those things will go. Whenever we need high performance, we'll go for high frequency and high voltage, so which will give the better performance. So, and as the power management unit, the power management is the main key point in low power verification. We have to properly choose the power management unit such that all of our clock gatings, power gatings, and everything will be taken care properly. And normally in a circuit, this is the main one which will dynamically turns off and turns on the system, depends upon the requirement. And next one is dynamic voltage and frequency scaling. So that is normally people call DVFS. So depends upon the performance requirement, we will change the dynamic frequency and voltage. So if it is less performance, we'll go for less voltage, and for high performance, high frequency. So, but this, if you're going for lower frequency, then your circuit and everything has to be taken care. So the voltage switching and frequency switching, just imagine I have something like hold and setup time has to be made. So all these circuits has to be taken care. So which comes at a cost of I mean, we have to increase more. We have to include most of the low power devices, which comes at cost. So everything has to be taken care. And next is the power supply integrity. So the power supply integrity means like I'm supplying a power to it. So, but because of this switchings and those things, I will see some disturbance. We can observe some disturbances in the power supply. So we have to make sure that power supply has very less spikes like those are a continuous power supply. It's not like abrupt power supply increase and decrease, which also can contribute to power loss. So that we have to taking care. And last but not least, the design testability DFT for low power devices. It's not like normal IC. So for low power, we have to insert the DFT, which is I mean, it's not much more difficult for that rather than normal IC. So that has to be taken care. So DFT insertion is pretty much uh, we can do for some of the circuit, but not full circuit. That has to be taken care, and we have to plan accordingly because it's the power of one of the we have this device also, right? So it will make some bit I'm thinking something difficult. So these are main design issues and their explanations. And so next comes the what is the issues and their debugging strategies. These are like isolation issues, um, and level shifter issues, retention issues, and miscellaneous low power design issues. So comes to isolation issues like I want to go. I want to. I mean, I want to create some isolation between the circuit, but because of it's going to different clamp value, so which also can cause issue. And that means I disconnect the power port from low. I mean, I disconnect the port, but I can see some value on it instead of I just want to make it so power getting. So I switch off that cell, but I can see some value on it. So that is the one issue. Like so, and then is like even though I switch it off, I can see some transactions on it during the I mean turn off period, and even though uh, and while I'm restoring it instead of just imagine instead of 5 volts, I'm giving 3 volts, which is wrong. And there is a one more thing is like isolation control also we have there, right? So that's isolation cells we have some issue. Then the control will turning on and off. That also can consume power. Uh, and isolation turned off, power shut off. So this is also one of the issue. So this I mean, during the power shut off, we have the option to whether we have to check whether the isolation can be turned off or not during the power shutdown. So that also one of the issues. So sometimes people will think that even though turn it off, the power isolation should be there, but it's the data will be corrupted and the whole circuit will get go. So all these things has the main isolation issues because of for the isolation cells. And there comes the next thing is like okay, while designing one more thing is the level shifter. Level shifter means like my one circuit is working at 5 volts, another circuit is working at 1.2 volts. Then in that thing, the value shifter, I mean, whatever the zeros ones are coming, they will be changing from one voltage to another voltage. Those are called level shifter issues. So in that sometimes people won't think like we have to give the use a multiple level shifters, so which cause the missing level shifters in the designs, which also can cause the issue because people won't think it. And one more thing is like incorrect level shifting inserted. So incorrect means like instead of going for 1.2, I mean 5 to 1.2, I'm going to 3 volts like that. Then also that also can cause the issue. So these are the issues we have to taking care while shifting while inserting level shifters properly. And then retention issues. Retention issues means like when the isolation cell is placed, it has to retain its values. So during the retention protocol, master to slave configuration issues for master to slave configuration, retention protocol issues for master to slave configuration. So master is sending, so now I kept my slave in the uh, retention time, but because of some wrong configuration, it is going. I mean, during the isolation, starting of the isolation, I kept in the retention of wrong value. Then the slave will be configured into some other value. So that also is one of the issue. And one more thing, value mismatch in saved and restored values. So doing the saving, I kept some value. Doing the restoration, the value can be other value. So that also has to be taken care. And there are also some low power design issues, uh, like clubbing together, those things. Uh, yeah, these are the low power design issues. And now comes the power profile and power analysis thing. Now, how can we run? I mean, if you have any UPF or something. So what is the power profile and what is the power analysis? How to generate? How to know what is thing? The power profile. This is the flow for generating the power profile. Generating power profile runs in parallel. Like if my circuit is there, so I just want to do the power profile and power analysis. Just want to know how much power it is consuming and how it is running, whether clock getting is happening or not, how much power consumption. So during that power, so that is that type we call is like a power profile and power analysis. Normally to generate that one, we run the simulations in parallel. Simulations or emulations in parallel, and we collect the data. So depend upon the collection of data, um, we will evaluate the power profile and power analysis. Normally, there are two things. One is like a sampling time. So for this particular time period, like 1 millisecond or 2 milliseconds, we will for shorter period normally 1 millisecond. Here you can see. So that sample period we decide, and during that period, we'll just calculate the average power and we'll check the activity. So then we'll comes to know, okay, this is the power it is consuming, or some in the middle of the we'll run some application, and in the middle starting to ending we will take the data. So how much is it is taking the data. That's how we have two things to take care during the power profiling and analysis, just to evaluate our power. And next comes the path-based UPF. uh, so this is like a um, power formats. This is like a UPS means like universal power format, where we can see where to insert the cell, where not to insert the cell, what is the current new trends in the UPF strategies. So this will be pretty much useful when we are going for low power process. Currently, we are in path-based schematics. This is a recent advancement. So in the path-based UPF strategies, we have to mention where we have to introduce isolation, level shifter, and repeater strategies, uh, using ad hoc methodologies such as port splitting, which made power management very difficult. So in path-based, now in isolation strategy, specified and port support, fan out is going multiple receiver. Just imagine, I will just give a brief thing about you. So this is the circuit, my basic circuit. Here I want to insert in some isolation cell. Here I can keep isolation cell, which will be sometimes, which is good, but I want to have, because of the fan out, there'll be a lot of fan out, single isolation cell can't be put out. So then using the path base instead of port based schematics are a little bit complex to go on. So that's where going for path base. So depends on the path, depends on the utilization. We will write our UPF strategies so that we'll get the better low power optimizations and everything. So these are because these also contribute to our low power strategies and everything. So that's normally these are like path-based strategies. During the path-based strategies, we have isolation strategies and location fan out. Location-based strategies like fan out and self and parent. I will show you those strategies in the next slides. Uh, the example, this is the example design. So in this example design, I want to have like a path-based strategy for this one. So then these are like examples of how can we place. So you want to place minus location self in a UPF doing then it will place here. So it is giving more complex, or more easy for you to give where to keep those things. So and minus location parent. So here it's keeping in a parent location, and so manage location fan out. So depending on the fan out, it is keeping the things. So those things. And This is the path-based UFO examples here. You can see these are getting inserted here, depends upon our requirement. So no, so we are avoiding this glue logic. So it's unnecessary. If we keep it here for the circuit, then it is keeping here also in the port base. So we are particularly in this path only we're mentioning. So mentioning like we have only these things. And now comes the coverage. So while doing the coverage for low power, we have to, this is totally meant for verification, guys. So whoever want to do these things, we have to take care whether all text bits are generated, complex interactions are happening up or not. Yeah.
Pavan, you have 3 minutes left,
sure.
so you should start wrapping up, please.
Yeah, sure. Yeah. So all these things are challenges. Main challenges are there in here. So these are like a very small things about how to write, what are the types we can use, these things, the HCL functions, what we can use. So, and comes to here like dynamic power verification, like if you go for dynamic power verification, you have depends upon the requirement. The clock domain crossing, you have to take care DVFS, otherwise it will make your setup hold and setup correlations go wrong. So you have to take care those things here. While inserting the isolation cells, you have to take care them properly during the DVFS switches. Otherwise, it will cause you all the violations, because every time in the UPF you have to mention whenever there is a thing isolation cell, you have to take care as a new separate CDC path, clock domain crossing path. Otherwise, it will cause you issues. So yeah, thank you. Any query?
Thanks, Pavan. We have time for just one question. So I'll read the question, and then if you can answer in a couple of minutes, please. You have mentioned the trade-off between performance and power. Isn't power one of the performance metrics itself? In the context of your talk, how is performance defined, please? Latency, other metrics such as area?
Mike, I can answer that. The thing is in this 5 context for the SOC we are making, there are 2 things. One is called power dissipation and energy consumed. That's why what we mean is performance metrics. That has nothing to do with the area, but with the energy intervals for the timing-based power analysis.
Yeah, but the trade-off between performance and power, which type of performance are you mentioning?
The thing is, there are some segments which are not switching but are consuming a lot of static power, and there are some segments which are switching a lot but static power is less. So we have to do a trade-off between these 2 segments.
Yeah, the question.
That's why we choose path-based.
What are you measuring? So sorry, the question is, what are you measuring as performance? Are you measuring latency? Are you measuring clock speed? Are you measuring instructions per second? What's your definition of performance in this?
All 3 of that, and the last one is more important. Instructions per second. That is the one which gives the benchmark.
Okay, instructions per second. Okay.
Yes.
Okay. So thank you very much to Pavan and Sathinder. Thank you very much for your presentation.
Thanks, Mike, and the team.
Thanks, Mike.
Okay.